All right, let's dive in. Today, we are tackling a data structure that, let's be honest, can feel pretty intimidating: graphs. But here's the thing: I want to completely reframe how you think about them. Forget complicated. Let's start thinking expressive. I'll show you what I mean. When we first start learning about this stuff, we get these really nice, tidy data structures, right? You've got arrays, which give you this perfect, predictable sequence, one thing right after another. Then you have trees, which give you that clean parent-child hierarchy with a single root where everything starts. It's all very orderly. But here's the catch: the real world is almost never that polite. It's messy. It doesn't fit into a neat line or a simple family tree. Just think about it: your own friendships, all the cities connected by flights, or how ideas just link together all over the internet. It's not a line, it's a web, a huge, tangled web of connections. Okay, so here's our game plan for today. First, we're going to see exactly why those simple structures just can't keep up. Then we'll break down the anatomy of a graph, what it's really made of. After that, we'll get into the fun part: designing and navigating them. And finally, we'll pull it all together to see why this way of thinking is such a game changer. And that brings us right to our first big idea. When the old models just completely break down, we need a totally new way of looking at things. We need a structure that isn't built for neat order, but one that's built for, well, for connection. And really, that's the punchline. When you're dealing with a system where pretty much anything can connect to anything else, that's when you need a graph. It's the perfect tool for the job. You could even say it's the native language of interconnectedness itself. So, what is a graph really? Let's just strip it all the way down to its most basic parts. And trust me, it's probably a lot simpler than you think. At its absolute core, a graph is just two things. First, you have nodes. You might hear them called vertices. And those are the individual things: people, cities, products, whatever. And second, you have edges. Those are just the lines connecting the nodes, representing the relationships between them. Think of a friendship, a flight path, or one of those customers also bought links. That's it. It's a model built purely for relationships. Now, this is where it gets really cool. This is where graphs just throw out the rulebook of those simpler structures. There's no required starting point, no root node. You can have cycles, where A connects to B connects to C, and C connects right back to A. And there are almost always multiple ways to get from one point to another. This is the big trade-off. You give up a little simplicity, but what you get back is this incredible expressive power. So you might be asking, why even bother with all this complexity? Well, it's because in so many real-world systems, the relationships are the most important part of the story. Think about a social network. It's not about where you are in a list, it's about who you're connected to. Or a map. The paths between cities are everything. In these cases, the connectivity is the meaning. And this leads to a really key insight. An array or a list, that's just a collection of items. But a graph? A graph is a description of an entire system. It shows how all the pieces interact and influence each other. That's a huge shift in perspective, right? Okay, so we've got the what and the why down. Now let's talk about the how. Because graphs are definitely not a one-size-fits-all kind of deal. You actually have to design them specifically for the problem you're trying to solve. So the first big decisions you have to make are about the relationships themselves. Like, is it a one-way street, like following someone on Twitter? That's a directed graph. Or is it mutual, like a Facebook friendship? That's undirected. What about if the connection has some kind of value, like the distance between two cities? Well, that's a weighted graph. These choices you make up front totally change what kinds of questions your graph can actually answer. All right, next up, how do we actually store this thing in a computer? Well, there are two main ways. The first is an adjacency matrix. You can just picture a big grid. It's super fast for checking if a connection exists, but man, it can eat up a lot of memory. It's best for dense graphs where almost everything is connected to everything else. The other way is an adjacency list. This one's way more memory efficient and is perfect for sparse graphs where nodes only have a few connections each. This is a classic textbook engineering trade-off: speed versus space. And this is such a perfect example of a fundamental truth in engineering. How you decide to represent your data, that is your very first and honestly probably your most important optimization. Get it right, and your algorithm will fly. Get it wrong, and the whole thing can just grind to a halt. Okay, so we've designed our graph. We've chosen how to represent it. It's this beautiful model of a complex system. But now what? How do we actually use it? I mean, how do you find anything in this big web of connections? The answer is something called traversal. There are two main ways to do this. First up is depth-first search, or DFS.
I like to think of this one as exploring a maze. You just pick a path and go as deep as you possibly can until you hit a dead end, then you backtrack and try another path. The other one is breadth first search, or BFS. This one is way more methodical. It explores all of your immediate neighbors first, then their neighbors, and so on, moving outward layer by layer. So DFS is awesome for just discovering the shape of the graph, while BFS is your go-to for finding the shortest path between 2 points, as long as the graph is unweighted.
But here's a heads up. Traversing a graph is a lot trickier than traversing a tree. And why is that? It all comes back to those cycles we talked about. If you don't keep track of which nodes you've already visited, your algorithm could literally get stuck running around in a circle forever. You absolutely have to be deliberate about it.
And that leads us to a really important engineering insight. Working with graphs, well, it punishes sloppy thinking. It demands discipline. You have to manage state. You have to track where you've been. And you have to guarantee that your process will actually end. They are incredibly powerful, but they have no tolerance for carelessness.
So we've covered the mechanics, right? Now let's zoom all the way out to the big picture. Why is this way of thinking so incredibly powerful? What does it really unlock for us? This little comparison here really puts it all into perspective. Trees are hierarchical. They're safe. No cycles, unique paths. It's all very predictable. Graphs, on the other hand, are relational and incredibly powerful. They embrace cycles and multiple paths. So with a tree, you get limited but simple expression. With a graph, you get massive expressiveness. But yeah, it comes with a bit more complexity. And this is the first huge takeaway I want you to have. An array forces your data into a line. A tree forces it into a hierarchy. But a graph doesn't impose a structure on anything. Instead, it just provides a canvas for the real, inherent structure, that hidden web of relationships to reveal itself. And here's the next big one. If you can model a problem as a graph, you can usually solve it. This is such a profound idea, and it goes way beyond just computer science. The very act of framing a problem as a graph, of figuring out the nodes and the edges, that process itself often lights up the path to the solution. It's like a universal problem-solving tool. And that, right there, is why graphs sit at the absolute frontier of modern systems. From mapping the human brain, to optimizing global supply chains, to powering the recommendation engines that literally shape our culture, graphs are the single best tool we have for making sense of the complex, interconnected systems that define our world today. So, I want to leave you with a question to chew on. Take a look at your own world, your work, your hobbies, your community. What are the nodes? What are the edges? What hidden connections, what underlying system is just waiting there for you to finally see it as a graph?